Today we are going to look at another example of structural analysis of a single rigid body in 3D. As we mentioned before, there is nothing special about it, just that you have to be a little bit careful about how you set up your calculations, and there is more chance for you to make numerical errors. So let's look at another example where we do this kind of thing. The problem that we are looking at is a crank, something that winds up this big crate. So the weight was 75 kilograms. That's the mass of this thing. So the weight is 75 kilograms times 9.81 newtons. Okay, and what we are required to find is how much force does it require, and there are two bearings, B1 and B2, A and B, and we want to find out the forces on these bearings. From a design perspective, the size of the shaft and the forces on the bearings are critical, because that's what we use to find out what bearing should I buy. And what shaft should I use? So that's the reason, that's the higher level idea. And if you remember your notes on different kinds of bearings, remember that if the bearings are properly mounted, this is how we are going to do the design. We are going to assume the bearings are properly mounted. Then if they are properly mounted, then there will be no moments on the bearings, there will just be forces. So it's actually fairly easy to calculate. So we are going to draw a free body diagram of this thing, and we are going to find all the forces on it. Okay, and then we are going to do a systematic force table. There is nothing, this is a very straightforward problem once you draw the free body diagram. Okay, so let's get to that. So I'm going to draw this free body diagram. So notice I don't draw it directly on the picture. So this is Z, this is X, this is Y. So here is the shaft. There's the shaft. Okay, at force, there's a force here, that's F. This is point C. At point B, now remember, this is at point B there is a simple bearing, so which means that there will only be sideways forces. So there will be a sideways force in the Z direction, which will be called BZ, and there will be a sideways force in the X direction, which will be called BX. No BY force. That's what bearings do, and no moment. Okay, at this, whatever this funny shape is, there is a force here. Let's call this point D, and the force here is 735.575 newtons. And then at point A, we have there's a Z force AZ, there is a X force AX, and there will be a axial force AY. Thrust bearing. We are done. Free body diagram is over. So this is A, that's B, that is C, D, X, Y, Z, everything is there. We are going to list all the locations. A is 0, 0, 0. B is, we will need this, no? So X component is 0, Y component is 1.1, Z component is 0. C is, X component is 0, Y component is 1.2, Z component is minus 0.2. This is all meters, and then D, X component is 0.1, Y component is 0.6, Z component is 0. Those are our locations. We are ready. What I want you to do before we continue, please pause, draw this free body diagram, write out all these things, because I want you to follow along with me. Okay, now we are ready to set up the force table. I'm telling you, there's nothing to it. Okay, especially in problems like this where there's not even a trigonometry, there is nothing to it. We are off and running. So let's do this. Okay. Okay, so now we drew all these things. Now I know that at A forces at A look like AX, AY is AY and AZ. Force at B, BX, 0, BZ. Force at C, F, 0, 0. Force at D, 0, 0, minus 735.575. Done. And then we already had all these locations. A 0, 0, 0, B 0, 1.1, 0, C 0, 1.2, minus 0.2, and D 0.1, 0.6, 0. We have converted the entire thing into vectorial form. We are done. Tick. Off we go. We set up the force table. That's what we do next. Here it is. So I'm going to write this down. Point A, 0, 0, 0. I want to make sure that all the numbers are right. So let me make sure of that. So this is AX, AY, AZ, 0, 0, 0. No concentrated moments. There is no problem. B, 0, 1.1, 0. BX, 0, BZ. So you will get 1.1 BZ, 0, minus 1.1 BX. You know, moment in x direction is YFZ minus ZFY. So YFZ minus ZFY, you know what to do, right? And then C, 0, 1.2, minus 0.2, then F, 0, 0. So it will give me 0 minus 0.2 F, 1.2 F. I'm doing this really fast. What I want you to do is do it slowly and look at all these numbers. If you don't do it, you're just watching somebody, you're watching an exercise video. I am getting better. You are not. So please remember, you have to sit and do this. I am just showing you what you should get when you do this. And maybe you don't get this because I have a sign error or you have a sign error. So it's time for you to check and make sure that I am right. So point D, 0.1, 0.6, 0, 0, minus 735.575. Sorry. There you go. See, I made a mistake. I put it in the wrong place. That's a Z force. That's not a minus 735.575, and then you will get minus 441.45, 73.575, 0. There you go. We have finished our force table. How about that? Of course, I did it fast because I have already done it on the side here. My book is here, so you can see I have done this. And this is not the first time I did. I did this again and I got it wrong. So I just want to show you that I also make lots of mistakes. You can see that my force table has lots of mistakes, right? So don't be afraid of making a mistake, but figure out how to fix it. So now my equations are, the sums are this, 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 this. I'll get 6 equations and we'll see if we have enough unknowns, and then off we go. That's it. So let's do that. 6 equations. Equation number 1, sum of all the forces in the x direction equal to 0 gives me was minus 0.2 F. Sorry, apologies, that's not the right equation. This is the right one. AX plus BX plus F equal to 0. That's equation 1. AY equal to 0. That's equation 2. AZ plus BZ minus 735.575 equal to 0. That's equation 3. 1.1 BZ minus 441.45 equal to 0. That's equation 4. This is summation of forces in the y direction equal to 0. So x goes like that positive, y goes like that positive, z goes like this positive, and then summation of all the moments along the x direction equal to 0. So that's that way positive. That gives me that. Summation of all the moments along the y direction equal to 0. That's that way positive. And I will get minus 0.2 F plus 73.575 equal to 0. That's equation 5. And then summation of all the forces that way positive. Summation of all the moments equal to 0 gives me minus 1.1 Bx plus 1.2 F equal to 0. That's the sixth equation. So if you have a calculator, just 6 equations, and let's see how many unknowns I have. Ax, Bx, F, that's 3. Ay is 4. Then Az, Bz is 5 and 6. And then there's no new unknown here, no new unknown here, no new unknown here. 6 equations, 6 unknowns. Nothing, no need to panic. If you look at this, start out with equation 5. From 5, you will get F equals 368 newtons. Straight, you can solve that. Then from 6 gives me Bx equals 401 newtons. Sorry. (401 newtons). Then you will get from 4, you will get Bz equals 401 newtons. Then from 3, you will get Az equals minus 769 newtons. That means it's pointing in the negative, it's pointing downwards, not upwards. And then from 1, you will get Ax equal to Bx plus F. So it turns out to be Bx plus minus, sorry, this is Ax, I'm sorry. And then I'll get Az. What is Az? Az is Bz minus 735. So Bz is 401 minus 735. So that's about 334 newtons. We found everything. Of course, Ay was 0. And of course, see what I mean? We found all the answers. It's pretty straightforward. There is nothing to it if you systematically follow the force table. So the trick is draw FBD properly, pay attention to bearings, if you do the force table, it will save you time, recovery from errors. 3. To do the force table, so maybe I should put that up here, but to do force table, maybe it's better to list force position vectors and force vectors and then enter, and then Think about solution strategy. Okay, think about which equation to solve first. Try and do, typically start with moments first. That's a strategy. Turns out that typically speaking, it's better to solve moment equations than force equations first. If you want to know why, because if you are clever, you can always get all the equations by just doing moments. If you are clever, you don't have to be clever, but at least you should stare at your moment equations first. So just to make sure you understand what I mean by this statement, if you go back, see, before this was my force table, right? Before I did this force table, notice I wrote down my forces and so I have to be careful. I wrote down my forces and I wrote down my position vectors A, B, C and D. This will help you make your life much simpler, because then you can copy it down pretty easily. Okay, and my force vectors, the main pain is these three: likely, sign and other errors. And unfortunately a calculator is no use, because some of them are symbolic. So you have to do this and you have to check it. There is no way out. Force vectors, make sure you enter things in the right places. Don't mess around with that. Pay some attention. Okay, this is very important. So these are the typical places where you are likely to go wrong. Thank you very much.